Okay, so my name is Alberto Gonzalez from STAR Barcelona. I'm going to talk about the SpaceFibre for FPGAs. So the IP is available, and also the results from the radiation test we undertook a collaboration with Microchip. Okay, so SpaceFibre, for those of you who are not familiar with SpaceFibre is a spacecraft on board data link and network technology. So it provides a high performance, high reliability, and high availability inside the satellites. So it runs over electrical and fiber optic cables, and is an approved ECS standard. So it was released in May last year. So SpaceFibre is high performance, so it runs more than 3 gigabits per second in current flight technology, like the RTG4 or the Virtex5 QB, and in more than runs above 6 gigabits per second in new generation radiation-tolerant FPGAs, such as Kintex Ultra-Scale or semi-polar fire. Supports multi-laning up to 16 lanes, and hot and cold redundancy is supported with multi-laning, so this adds to the high reliability of SpaceFibre. And then you have the quality of service, and also there is a novel integrated fault detection, isolation, and recovery support, which provides high availability. And the transient errors are transparently recovered by the IP itself, the protocol, so the user doesn't really notice. Okay, so what do you need if you want to build a SpaceFibre network inside a satellite using FPGAs? So you need building blocks, so IP cores. And STAR-Dundee provides a set of building blocks. So the basic one is a single lane interface, which is very easy to use, and no prior knowledge of SpaceFibre is really required. And also SpaceFibre, one of the advantages is that it's compatible at the packet level with SpaceWire. So connecting SpaceWire packets into, sending SpaceWire packets into SpaceFibre is, straightforward. And we have tested the IPs, the maximum speeds in the RTG4, the Virtex5, and Ultra-Scale and Polar Fire. The IP is highly configurable, so it gives flexibility through the use of generics, okay? And it automatically recovers from transient errors in less than 3 microseconds. This is why the user doesn't really notice, because there are small recovery buffers inside the IP, and everything is managed by the IP itself, so it's transparent to the user. And then there is the multi-lane interface IP. So on top of the features of the single lane, the multi-lane also provides a configurable number of independent lanes. So any number between 1 and 16 can be chosen. And also they can be configured as cold or hot redundant, depends on the, up to the user to do that. And then of course, this multi-lane offers automatic graceful degradation in the event of lane failure, which means that when a lane fails, if they are not whole or core redundant or selected, then the lane bandwidth is reduced, but higher priority virtual channels, the higher priority traffic is less affected or not affected at all, depends on the available bandwidth. Hot redundant lanes recover really fast in less than 3 microseconds from lane failures. And this is automatic, so there is no user intervention. And unidirectional lanes are also allowed to save power and mass. Finally, last building block required would be a routing switch to connect different nodes using SpaceFibre together. Our routing switch IP is built around an unblocking routing switch matrix, and is fully configurable. And any number of ports are supported, and different types supported too. So you can choose between SpaceFibre or SpaceWire or FIFO-like ports. FIFO-like are for, using them inside the same FPGA design, for example. And for SpaceFibre and FIFO-like ports, any number of virtual channels are possible. And a virtual channel is a concept that SpaceFibre provides, and is a way of sending different data streams inside the same physical link and in an isolated way. So thanks to the quality of service, all these virtual channels can be isolated one from the other, and if something happens in one virtual channel, doesn't affect the rest of them. The router also provides a configuration port that uses your map to access the memory space, and the single lane routing switch IP is already available, and the multi-lane will be by the end of this year. In the images, the different IPs running in different FPGAs, PolarFire, RTG4. We are now working also on the Nano Explore Brave Large. And in this table, you can see a rough idea of what each IP, the number of resources required for different FPGAs. So you can see that the single lane interface is really small. Doesn't really require much in an FPGA. For the multi-lane, it takes a little bit more resources, but keep in mind that in this case, this is for a 4-lane link. So it means that you have 4 times the bandwidth available. And of course, you have the additional capabilities such as graceful termination or functionality. And finally, for the router, you can see that it takes current technology like 30–40% at most, but keep in mind that this router is an 8-port router with 8 SpaceFibre ports, 2 virtual channels each, which is quite a big design actually, and still you have a lot of space available on an FPGA for other blocks if you want to introduce them. Okay, so this will be the reference for the IPs, and now let's continue with the test campaign, radiation test campaign, and the results. So we performed this test campaign in Texas TAMU facility in collaboration with Microsemi, and the main objectives of the testing was to evaluate sensitivity of the RTG4 SerDes to radiation, and also the robustness of the SpaceFibre protocol itself against radiation effects on the SerDes, and the STAR-Dundee SpaceFibre IP core sensitivity. And finally, to evaluate also the specific SerDes reconfiguration module performance. So we STAR-Dundee developed a SerDes configuration module to recover from single event upsets in the SerDes configuration registers. So this is the test setup, a simple diagram. So we use all the SerDes available in the RTG4, and due to limitations on the hardware side, only one of the SerDes was connected to an external device, in this case a multi-lane Starfire device. We use a SpaceWire to record and to take out the test information, statistics, and 2 SerDes were used only for monitoring the SerDes effects, radiation effects, and for also monitor the SpaceFibre too. An image of the board, and you can see on the right the board inside the radiation chamber just in front of the beam, and how it looks like. Okay, so what about the results? So there was a small, well, not small, an operational issue. And what happened is that we were using the internal oscillator and the clock conditioning circuits of the RTG4, and the log signal of these devices is glitches with radiation. So there are a few glitches on the signal sometimes, and the problem is that these signals were used to reset the control logic and also the SpaceFibre IPs. So of course, these glitches were causing to the control logic and the SpaceFibre to be reset from time to time due to radiation, which isn't good. But fortunately, we managed to narrow down the problem, and we successfully shielded this affected the internal oscillator and the CCCs, the clock conditioning circuits. And some of the data was compromised, but some of the data, the most useful one, wasn't. So well, we were, fortunate in that regard, because those components were in a different location than the rest of the design, so it was possible to shield them. Okay, so this is the SerDes clock section we obtained, and of course you can see that there is some data affected by these log glitches, okay, inside the orange circles. But what we can see here is that there were some error bars and bit flips, and as expected on the SerDes, and they are more likely at higher LEDs, as one can expect. But in this case, for the CDR loss of log, the values for lower LET weren't really to be trusted because of this log signal effect. So we saw on these low LETs that all the SerDes, all the lanes were presented loss of log at the same time. This was due to the lane being reinitialized because of these glitches, and also to support this theory also is the fact that when we shield them for higher LETs, we didn't see that many loss of log. So I mean, we will need more data to be sure that everything makes sense, but this is the most likely reason. In SpaceFibre, you can see here a picture of the cross-section for the different errors. So in this table, received error is the less important error, or the less severe in a way. And at the bottom of the table, data error is the most serious error in a way, because it means that an error has gone through SpaceFibre to the user without the user noticing. And well, you can see here that the CRC errors are very low, and the ADAC failure and data error probabilities of cross-section is almost the same. And one can infer from this data that probably all data errors, or most of them, were produced by the ADAC failures. And this is because our IP was, even in the event of ADAC failure, was passing the data to the user. But since then, we have modified the IP, and we would have fewer data errors, almost none, thanks to this improvement. Okay, so what about the throughput and the lane downtime? Because of course you have transmitting data, but if the lane is down and you are not transmitting anything, you won't have any errors. You can see that well, even for high LETs and high flags, the throughput was better than 99.99% during the radiation test, and our lane downtime was below 0.005%, so it was really good. And bit flips and most burst errors were recovered in less than 4 microseconds as expected, and some burst of errors required less than 3 microseconds or less for the RTG4 to initialize. But if you're using multi-lane, you recover the link in less than 4 microseconds, because you can keep going with the remaining lanes until the affected lane recovers. So SpaceFibre produced very good results. Okay, so as a conclusion for this dissertation, this talk, so in this plot you can see the performance of the SpaceFibre against the performance of the SerDes. So you can see SerDes data errors and SpaceFibre data errors. So you can see that there are several orders of magnitude of difference. So in this case, SerDes data errors will be data errors of if you don't use any protocol, or a very naive protocol. Of course, you will have these errors grouped in bars usually, but still the average value will be that one. So now on the other hand, SpaceFibre produced really few, and the cross-section is very small, but still, and as I said, with the improvements we have done in the IP, thanks to these results of this campaign, we expect even fewer errors. So finally, to conclude, all SerDes were recovered from radiation effect without requiring power cycle and device reset, which is a very good result, because it means that in any case we ended up in a deadlock situation. So this means that the configuration module from start really managed to recover all the SerDes as expected. And also the radiation effects, of course, in the SerDes produce temporary loss of log and bit flips and burst of errors. So if you're not using any protocol to transfer data, this leads to a significant number of errors. But fortunately, SpaceFibre proved to be very robust against such effects. And well, multi-lane recovered from radiation effects in less than 4 microseconds. So this is a very good, very fast recovery. And yeah, most of the errors, as I explained before, were probably due to a DAC failure, the memories, because of the high flags. So with the improved version of the IP, we expect most of these errors to disappear. And finally, yes, there is another campaign planned to address all these issues and refine the data obtained. So hopefully this will be done soon, and yeah, we will have more and more reliable data available. Thank you very much. And this concludes my presentation. If you have any questions, feel free to ask in the live chat box below, and yeah, I will be glad to answer them. Thank you.